So maybe I have 50-minute presentation and 10-minute Q&A.
Oh, sorry. It really depends on your schedule. We can use the remaining time for discussion. Yeah. Maybe it's several minutes.
Discussion.
It's okay.
Yeah.
Okay. We hope we can have enough discussion. So, okay, it's time. Let's begin. So, how everyone? Welcome to the Urban Lifeline public seminar. Today, we have the Professor Dan Ji from Saitama University to give us a presentation about damage detection using UAV, 3D point cloud, and AI for bridge management. I'm Xinghao He from the Tohoku University. So before the starting of the seminar, please allow me to briefly introduce Professor Dan. Professor Dan is currently an associate professor at Saitama University and executive editor of the Journal of Urban Lifeline. Professor Dan is a member of JSCE and JAE, ASCE, and SSA, and many other associations, international associations. And his research interests include bridge engineering, earthquake engineering, bridge management, AI, UAV, IoT sensing, and DX in structural dynamics, structural health monitoring, and bridge maintenance. So in this seminar, we have around 1 hour for presentation and discussion combined. And depending on Professor Dan's schedule, the remaining time, maybe several minutes, we can use for discussion, question, and comments. In addition, I want to mention that Professor Dan is a pioneer in exploring the application of AI in civil engineering problems. I still remember when I was a student about like 10 years ago, before AI became popular in civil engineering, he had already started his research on AI. So he also asked me some questions about what's the difference between AI and deep learning at that time. So I'm really looking forward to his wonderful speech today. So let's welcome Professor Dan's speech. Okay, please start your presentation, Professor Dan.
Professor, thank you very much for introducing me. I'm very honored to have today's online seminar, and thank you all the audience to coming to listen to this online seminar. So today's topic is, as Professor introduced, my research interest currently greatly focused on AI and IoT and UAV. So today's topic is more focused on disaster prevention or damage elimination using AI and 3D point cloud technology. Today, I want to introduce something about damage detection strategy for structural engineering. As you know, that last year was the 30 years anniversary of the 1995 Kobe earthquake. So to this month, it will be the 31 years ago. So at that time, we had great damage, especially for the steel piers, local buckling. Before that, Japanese engineer believed that bridge was still so good. It's good enough that no need to be reinforced, but we got a lot of damage on bridge structures. So last year, we just have the 45th JSCE earthquake engineering symposium in Kobe, and to review the past 30 years of what we learned and what we progressed from this earthquake. So we visited Kobe, and also Professor I got also went there. So I found that a lot of piers was reinforced, and damaged harbor was kept as a park, and I even see some bridge using the base isolation in the basement of the pier. quite impressive change on that. After Kobe earthquake, Japan also experienced a 2011 Toho earthquake. This bridge was caught damage in Sendai, which is also very near to Professor He's location, I think. So found a lot of damage of isolation bearings. Same phenomenon also been found in the 2016 Kumamoto earthquake. The huge earthquake damaged the bearing part and also the main bridge part. But some of the bridge was damaged very seriously. But however, only one bridge was caused by landslide and finally collapsed. But other bridge somehow still kept on the place and prevented to the total collapse and preserve the functionality of the emergency transportation after earthquake. Also in 2025, we also have great earthquakes in Philippines, near to Japan, and in this earthquake, we find that some bridge also have the approaching part damage, which one of the largest earthquake recently happened. And so after the 2011 earthquake, so in the east side of Japan, have a lot of small earthquakes happening, and some of them are quite magnitude over 6. And also in Hokkaido and also in the Kumamoto area, also a lot of aftershocks. So after this earthquakes, the bridge was asked to do emergency inspection to make sure the serviceability is kept. And this is how this is not the earthquake emergency inspection, but is traditional inspection, bridge inspection in Japan. So we can see that for a large bridge, they need to be some transportation traffic regulation, and also need special machine to go under the bridge to check the bridge. And this is quite time-consuming, and all the operation have to be done at nighttime when the traffic is not so much. So recently, bridge inspection was shifting to like to use more new technology like UAV and other new technologies such as AI. And especially in the 2024 Ishikawa Noto earthquake, peninsula earthquake, we had a great shake, and many bridge also damaged after the bridge. We have captured over 1G shake on the ground, and but I can see the damage on the bridge was less than the Kumamoto earthquake, but still we captured some specters of damage of bridges. For example, in the twin bridge Noto, which is a very large bridge and cable-stayed bridge, and we can see in the end of the bridge there's a two-span side span bridges, which is concrete box girder, and the end of the girder was totally collapsed. I just heard from this year that engineers decided to rebuild the superstructure of the bridge of this bridge. So no just a small repair, but overall reconstruction of the two-span side of the bridge. And during the inspection of the bridge, we used UAV to capture some bridge damage directly after the earthquake. You can see the 3D structure reconstructed from the UAV images can reflect the very detailed part of the bridge in the surface. Also, we can observe even cracks detailedly on the surface bridge, of course, also on the damaged bridge. But however, we cannot see the inside. What's inside happened to the bridge from the UAV. This is a overall 3D model reconstructed for the bridge. This is the main two span of cable state span. This is the two span that have the box cutter. You can see in the middle pier, which is reinforced by FRP sheet, also have a base part. They have some cracks of the reinforced part. This is mainly caused by the bending moment on the pier. And we can also observe that the bearing part, the cover part was damaged, and also the end of the girder also been damaged from the UAV survey. So basically, to inspect this kind of huge bridge costs a lot of time to see from all over the angle to the bridge. And the overall survey needs some large-scale machines, a lot of human works to do. And unfortunately, the 2024 earthquake was happening in the January, and the weather that there it was quite cold. This one I was taken in the a few months later, but on site, a real-time photo and real-time survey will cost a lot of time and a lot of work to do. But if we use a UAV and to do just a few hours flight, we can see quite detailed information and can reconstruct the scene of the damage of the bridge. So the expertise can do some version inspection in the back side of the office. Also, I can see to go to the site of damaged bridge is quite difficult because after the earthquake, there's a lot of traffic jam because all the rescue team and engineers cars are all going into the area, and the gasoline station was quite strict on the regulation of the gas supply in the isolated area. And this is we also captured a town named Ukai, which is in this earthquake was damaged both in earthquake and also tsunami. You can see the seaside of the building, a lot of building was flushed away because of tsunami, and most of them was collapsed after earthquake. So it's quite difficult to do a door-to-door research, but from a UAV flight, we fly this UAV just 20 minutes, and we can reconstruction these areas, a 3D model in just a few hours. Then we can count how many building was damaged and what kind of damage they happened from very detailed 3D model. And we can also, some of the work members are also doing the calculation about how much the garbage was generated after the earthquake, because to rebuild this town, we need firstly to have some place to produce this kind of damaged garbages. And in this town, one of the bridge named Okai Bridge was also severely damaged, and our UAV flight after the overall flight, we also flight UAV for this bridge. You can see the sidewalk bridge was totally collapsed, and overall bridge didn't collapse but also severely damaged. Recently, near to Japan, there's a great earthquake and tsunami happened, and so this is also a warning alarm for us that next big event is coming, and we need to be prepared for this kind of large-scale earthquake. So to do so, we need to increase the tools, fast survey and fast evaluation and fast planning technology using UAV and AI. not only in the disaster time, but in the maintenance process, we should start to do 3D model reconstruction and a survey and to accumulate the data so that we can compare it with the bridge damaged when earthquake or other natural disaster happened. So for now, a lot of highway have this kind of rule that after the earthquake, we need to do two type of inspection. So one inspection is on-road inspection, which means engineers while driving a car or even bike or bicycle to go the upside of the road, to go through the road to see is there any big distance of the road and level distance between bridges. Another is to do underneath inspection, which is human engineers and inspectors that take a walk under the bridge to check the pier. Is there any damage or abnormality happens in there? And this is quite based on the skill and the judgment on the side of the engineering. And this is quite difficult to do a quantitative evaluation or on-site survey because in that kind of time, it's quite an emergency. So you cannot carry a lot of measurement machine like normal measurement survey work. Also, this kind of work also will be conducted in very short time. So you cannot to do a very detailed and well-planned survey like normal inspection. So here we propose to using three steps approach to do this kind of emergency survey. Firstly, we can under the bridge, we can also fly UAV to do bridge inspection and just took the photo after the earthquake. By the way, this picture was generated by AI also, but you can see that not very quite good, but you can get the imagination what I'm trying to say to you. The second one is to reconstruct the digital twin or 3D model that we can measure the damage and compare the difference, quantitatively evaluate how much damage we get. And the third one is to build a BIM model that we can analyze and evaluate how much the damage will cause the change of capacity of the structures. Traditionally, we use structure from motion technology. It means we take some UAV photos and identify the camera's location, alignment, and using the feature point to build a 3D model and then generate 3D point cloud. But recent technology, especially for the scene of computer games, for example, computer games or some PlayStation games, we all need to reconstruct a 3D scene of a special location or area. So this there's some research proposed to use AI model to build this 3D scene, which is a scenario that we have some 3D models and objects, and also the light, also maybe some smoke, and also the changing of the light and humans moving, and the shadows moving. All this kind of 3D scene can be reconstructed, and if you give a specific view, a point, and angle of the camera, then the AI model can generate a 2D reprojected 3D ray of projection to the camera, and then you can get a 2D images. Because this kind of rendering speed is quite high, so that you can do a real-time 3D scene walking through, so that you can look at not only in a static 2D image, but a moving to this 2D images, serial images that you can walk into the 3D scene. One method was called NERF, which is neural network based method. So we used NERF model to generate the 3D. You can see the left side, it was regenerated 3D scene by NERF, and it is quite real. That is almost the same with the image we take from the UAV. Also, from multiple this kind of 3D scene, we can also easily generate a 3D point cloud in quite density of this 3D inspection. So to detect damage, we use a few methods. One is use smartphone image and use the image to reconstruct the structure from motion to regenerate the 3D point cloud. And another method is UAV's image and use SFM to reconstruct 3D point cloud. And we also, samely, this series of photos, we also used NERF to regenerate 3D point cloud. And also we use a smartphone LiDAR to scan the pier. All of them was compared to a high accuracy 3D LiDAR scanner. They generated the accurate 3D model point cloud so that we can compare them. So we remove the scale, but the accurate, you can see that they can reconstruct the original point cloud quite real, especially the smartphone LiDAR get quite dense point cloud and quite good accuracy. Same with UAV SFM, but you can see smartphone-based SFM and NERF, they can give a good outlooking, but when they go into the process of generate point cloud, they have some errors and have some quite large error. So we squeeze the range of the point cloud, so we can see some empty area, which is the error of the point cloud was quite out of the range. Another method we propose is from 3D to 2D method. So this method is, we firstly have a 3D model. We can reconstruct it by smartphone or UAV photos or even a LiDAR scanner. And then next, instead of a traditional way to segment them in 3D model, we use, firstly, we project them to automatic photo. And then we use this specific surface and use AI to detect damage. So this is the underneath side surface of a bridge girder. We can see the AI can detect some of the corrosion, and this is the painting area for some areas. But still, some area didn't detect any damage yet. Same, we can do it for the four sides of the pier, which is traditional, quite difficult to do in 3D model because the shape of the pier is basically is like a wall shaped pier, and because of the distance of the peer-to-peer distance, quite difficult to take a whole surface image of a pier. But using 3D regeneration technology, we can project them to four surfaces, and we can detect damage one by one in 2D image instead of using the 3D point cloud segmentation. So before we have some research using 3D point cloud and the 3D model to do the semantic segmentation, but we found that in reality is that it's quite time consuming to train 3D point cloud semantic segmentation model to detect a very small scale of damage. And one of the reasons is to prepare this kind of database is quite difficult because you need to scan the bridge, and then you need to do the point cloud annotation, and then you need to train the point cloud segmentation model. So instead of doing that, we just do a 3D model and project them to 2D again, and then use damage detection. So the merit of using this method is quite obvious because firstly, the overall data processing time can be shortened greatly. To do a 3D model reconstruction and 2D projection quite easy, and always everyone can do that. And currently, if the method is proper, you can see the regenerated 3D model and their surface are quite detailed because we use the tiled model. And the also image also can do it in quite accuracy in the size, because we can quite accurately know the size of the bridge, so that the measurement of the bridge damaged area is also made it possible compared to the 30-point cloud. So 30-point cloud is quite difficult in calculate surface area, because you need to firstly define our surface, right, in the 30 work. So this is the merit of using this method. And as another topic is to use train AI to detect local buckling in steel pier, as it was 31 years anniversary of Kobe earthquake. Kobe earthquake is almost the only one earthquake that people observed real bridge local buckling damage. And I think one of the reasons is only Japan is one of the country that using steel pier very accurately, very actively. I see. Also, when I go to the capital airport of Beijing, I also see some steel pier was constructed on the highway. I think in Tokyo and Nagoya and Peking is an area that both have risk of large earthquake and also using a lot of steel pier. So when I visit Nanjing and other city in China, I think people are using RC piers more. Almost most of them are RC piers, and very few steel piers. Only, I think, in very limited area that use construction are considering using steel pier. One of the reasons is it's very expensive and the cost. And so detection of the local buckling is quite difficult from the 2D images. The reason is that the picture of local buckling is quite few, and we don't have a lot of building damage pictures that we collected from Nepal earthquake, from Turkey, Syria earthquake, from Japan's a lot of earthquakes. So because there are a lot of building RC building have damaged, masonry building was damaged. They have a lot of pictures. But for Kobe earthquake, it was 30 years ago. In that time, we don't have digital camera yet, and there's no image database for this kind of damage. And only very few information was preserved for now. So this is a great challenge. So in this research, we use vision transform model, and the other we use generative AI to generate some local buckling and to make the AI to understand by generated and both generated and combined with some pictures. And fortunately, in the past of 30 years, we did a lot of laboratory experiment of peers. So we get some, also get some pictures from our laboratory. So I take this picture when I was a doctoral student. So we can still use these pictures to do something good. So we separated to a few level of damages, level 1. And so you can see in level 1, there's almost no obvious horizontal or vertical force degrading. So with the development of local buckling, you can see the local buckling developed larger and more obvious. So in this stage, there's a lot of about 90% of the horizontal force will decreased, but you can still use it after reinforcement after earthquake. But later, if you level 3 is more severe local buckling, you can see the stiffener also local buckling happens. So the horizontal force capacity was decreased less than 70%. So this kind of bridge was generally considered to be depolished. Even they prevent collapse, they will be depolished after earthquakes. So so second step is to using generative AI to generate some damage. We only use this research. We only use prompt engineering that can generate some steel pier and generate some local buckling. So as I showed pictures before, the image generated by AI is quite absurd. But recently, I see some in the social media. I see some AI generate some videos and short videos quite high quality. But still, when we go to the disaster scene, they may not doing so good in generating images. You can see the sea side was different, quite absurd, and we can see it's a steel, it's not steel, right? It's iron surface, and we quite feel we use this kind of color. We will use paint them to white or paint them to other colors, so they have no painting, and we were not welding the pier with some connection like this, right? Quite dangerous to melt pier like this, and we now using rounding a pier like this. We have very sharp angle for steel pier. They are quite only concrete pier have this kind of rounded cross section. Especially for the people doing research in the steel pier, so they will feel, oh, this is a bad generation of pier. But still, this kind of basic idea is quite there. So basic cross section of a pier was local buckling. You can see this is level 2 local buckling, and this is level 2 local buckling, and this is level 3. Okay, so this is looked better than the one above the sea, and you can see that is under some urban areas. You can see some thing is falling down here, and you can see they cracked with some connection areas, and local buckling is quite not real, but still they transfer some ideas as both have cracks and local buckling on the base of the steel pier. Also level 3 local buckling, and this is another one. So none of them I feel quite real, but I hope the hope is that AI can learn what is local buckling and recognize the real local buckling on the damage. So in the training, we use the AI-generated model, but in the testing, we use a real data set, which is used with this observed in the Kobe earthquake in the real time. So this is the vision transport models training, and for training, we get 90% accuracy. So validation, we also get over 80% of accuracy. And so this is generally, if you get 80%, so it's quite good. So they predicted level 3 in 97%. So actually, in my imagination, that there is only level 2 because of the no relative deformation or something, right? And this is a real image, but this is specimen level, and they predict that level 3 image. But I think it's fair for the current state. So also we can make a smartphone application that help engineers to do on-site damage detection. And so we can use the proper interface and proper calculation of the residue of the state. So so this is I think this is basically for building. So first we can say outdoor assessment, and if this is safety, and we can go to the indoor assessment. If this is not safety, we're not entering. And for the indoor assessment, basically this research is focused on the RC building, that is in case. And so we will check some conditions, so to separate the process of the AI detection. So the inspection may not the expert engineering, or they are expert engineering. And they may check it is a high risk building or not high risk building, and also the square areas of the building is a large scale building or is a small residential building. And if it is yes, they can do a detailed assessment. If not, we just do a rapid assessment. So they will finally give a yellow or red or green detection in the indoor assessment with the help of the AI model. So for outdoor inspection, we use a YOLO model. I think in that time we use YOLO V8 model. Actually, the YOLO model is changing very much, but the contents, the model themselves may not change so much. So the AI model can detect the building. The building not it's full over the screen, but they will give a basic detection about safe to enter or not safe to enter. So this is some example. You can see this kind of building is near to collapse or already collapsed. So obviously it's not safe to entry. And but this one I think this is wrong, right? They can save they can safely enter them. And so sometimes AI also makes mistakes. And for indoor assessment, they will AI. We considering we should conduct structural damage or non-structural damage, and give them a type ABC detection. And for non-structural detection, we can detect is not significant in-field wall damage or is with some repairs required. So the classification definition is like the table. There's type O, type ABC. O means no damage. ABC is 3 level of damage. So C is most severe level. So for example, this kind of building will be less damaged, will be A or 2 O damage. So this kind of damage will be severe damage because level B damage, I think, because you see the cover spalling. This one will be C. I can see the buckling of reinforcement RC building. So this is the gathering of the database. So this database was gathered from past Syria and Turkey earthquake of RC building. So there's a lot of damage building on internet. So if you can see, this is a column, or you can see the steel bar. So it means that this is a structure member. So if you can see them like a wall, or you can now see, you can see the infield breaks. So this is the infield wall, right? So if you cannot see what is inside it, so there will be not significant infield wall damage. So we separate this manually. And so for expert, they may have some complicated calculation, but if we use a mobile phone, that can be easily done. So that we can detect, like use AI to detect is light damage, moderate damage, or heavy damage. This is a based on some international standard, TCP, for on-site detailed assessment of the building's safety area. So we use this standard to calculate, to do the overall evaluate for the building after their inside multiple images detection process. So here are some demonstration of the application. So first you start a project. You can do outlook detection. So they tell you now safety. So you don't. So finish. Start is finished here, and you don't need to go inside to do detailed inspection anymore. And so, oh, this is not safety at all, right? And so that you can locate them quite well. They can also output the detected report image so that you can put into the report to see the to generate this report in the later steps. So for the indoor assessment, and you can upload indoor damage. Oh, this is outdoor damage also. So you can select damage, and the user model can take the damage process. So to generate more detailed inspection report, we need to generate some language that from the image you uploaded, or you can use some method to do some description of the overall damage. So here we try to also use AI model to generate this kind of report. The basic idea is, firstly, we use AI image caption model. So this kind of model is you have a picture, so they can generate some word using some AI model. But in here, we use another approach, not like the traditional image captioning, but we have some image, and then we have some image detection, and we can generate some feature, and then we use image captioning model to generate some text word. And then we use, next time we will use a large language model to generate a more detailed description of the model. So here's a validation data. So here's the image. So the actual caption will be club structure was detected. And we use image captioning model, a few, I think it's backbone model of VGG, ResNet, Inception, EfficientNet, and so they generate some model. You can see ResNet Inception is relatively bigger model, and they generate the same caption with the true ground truth. The club structure was detected, and the VGG is quite bad result. Say no damage was detected. And the EfficientNet will say severe damage. Maybe they are talking about this one, but they ignored the pile of damage in here. Sometimes the structure prominent object for the forbidden important some detection part. And then we use attention-based model. So traditionally we use attention-based models like CNN. We use traditional CN convolution method. Right now, the transformer model of self-attention mechanism based model was also proposed, can generate larger and more accurate language than we did. So we use the standard named BRIP, which is generally used for the image captioning, and also for the some of the translation work. So then to detect the damage. So this is a nodal earthquakes image we someone put on the internet. So they can detect, say, one collapse structure was detected, and this one is no damage was detected, right? So quite well. So one collapse structure was detected. Actually, they are this one damage. So actually, this one also collapsed. Sometimes they didn't focus on the real ones. So so we realized that we cannot only depending on image, but we should also give some other information to the model. So we call this non-visual information to helping the AI model to generate better description of the damage. So one of the most important information is using the earthquake information, such as PGA, PGV, the damage area. So as USGS will publish very quickly about PGA or PGV distribution of damage area after earthquake. Actually, they are published just a few hours after the damage. So we can, when we do the survey, we can use shaking map and PGA distribution map and information inside the image to tell where the location it is and to generate better description of the building. So the case one, so we set a few case so that like large language model like ChatGPT to generate some models. So you can see that even we use same model, we can give the PGA, building age, and image caption get by or image caption model, and deep learning prediction is now safety or some of this kind of information to ChatGPT. Then the ChatGPT can generate some quite nice suggestions for this kind of situation. And so because of time, so I will wrapping up my presentation. So the disaster happens not only for the earthquake, but also for the deterioration of the infrastructure. So for example, this is 1 year ago that happened in Saitama. It's the location called Yashio, and the drainage pipeline was corrosion and damage of the concrete, so that the earth was flowed into the pipeline and flowed away, and gave an empty hallway and caused the collapse of the road. Similar accident also happened in Bangkok, Thailand, recently in September last year. So yeah, in the middle of the city, and this is quite shocking accident happens. I think every year all over the world happens this kind of accident because of the soil was flooded away by the underground or pipeline or some leaking of the pipeline or some reason. Also, due to the erosion of the bridge caused after by the large rain, there's erosion of foundation of the bridge piers. For example, this is the one damaged bridge, and after the heavy rain, the fundamental foundation of the bridge was scored because you can see the flow was directly go to the bridge. Two sides of the river was quite reinforced, but the foundation of the bridge was quite weak. And so we use a 3D model to reconstruct the bridge to detect the erosion of the bridge. This is another bridge that erosion scored by heavy rain. You can see the foundation was exposed, and then we have a 3D model and to reinforce them. And this is before the reinforcement, and this is after the reinforcement. So we use UAV to reconstruct this two before and after 30 point. and we generate DEM, which DEM is just when you have 3D model, you split the whole area's map and to generate the height of each grade. And by comparing the DEM of 2022 and 2024, we can see these areas of the bridge was quite erosioned again. And this part was reinforced part and quite good. But if we do not reinforce this part, it will be damaged to bridge furtherly. So there's another bridge happened of the erosion, which also happened in Kenya. And we, from the 3D model around the bridge, we can measurement the area of erosion before and after the big disaster. So I think this part is repeated before. So this method is to take UV of the bridge before the disaster, for example, for the maintenance inspection, and then compare the 3D model after the damage. So I think this is all my presentation today. Thank you very much. So I will be very welcome. So if there's any questions.
Okay, thank you very much for Professor Dan's informative presentation. So now we come to the Q&A. And if you are using the WeChat live streaming, you can leave your questions and comments. I will read your comments. And if you are using the Teams, please just click the unmute button and ask your question. So firstly, I noticed we have a question from the WeChat channel from the Stamka. Okay, he asked when segmentation of the bridge is needed, are there any existing 2D bridge label database or label components? So can you address his questions, Professor Dan?
Yes, thank you very much. I think for bridge segmentation topic, so there are a few different missions currently. One of them is a component segmentation. In this part, I mean 2D image, right? 2D image. So we published some paper and we opened some 2D damage segmentation database, which is based on the Japanese bridges, and they are free to download. And but for 3D part, point cloud segmentation will be quite tricky. So we didn't find any currently useful damage detection segmentation. I think Professor Narazaki in the Japan University is doing some this kind of related work, and in his work, I think he did generated a huge 3D point cloud model to do the structural members segmentation, and I believe currently he are also focused on the damage part, but I didn't know how much and how can we download this kind of database yet. And segmentation is quite exhaustive work. So if anyone knows such related information, please let me know. I'm very happy to use it.
Okay, thank you. I hope this addresses your question, Samka. So is there any other questions? So I think Professor Dan provide a quick overview of recent earthquake disasters in Japan and the corresponding damages to bridge. These observations highlight the importance of bridge inspections. And then he introduced some advanced bridge inspection techniques combining the UAV, 3D point cloud, and AI technologies, and with several successful applications examples in post earthquakes. So now we have a question from the Yanxu. So please unmute yourself. And okay.
Yeah, thank you very much for Professor Dan for the very interesting and impressive presentation. I have one question. I know we all know that for the imaging and point cloud data, they can offer some information for the post-earthquake evaluation.
Yes.
So I would like to know what's your opinion about the role or the contribution of these data? Are they just offering an efficient option compared to the conventional visual inspection, or can they offer more information about the bridge conditions? Because we know that currently from the manuals, we are using component level rules for the ratings. Nowadays, we have the point cloud data. We can have the model. We can also have some like a crack or surface damages. Can we have like can they offer a new evaluation pipeline?
Yes.
Thank you very much.
So I think basically your question is about a 3D model are doing better work than traditional work. So basically, I believe the advantage of using 3D point cloud and 3D model, 3D information is firstly it's very fast. So you don't need to go to the real site and to do the inspection. So nobody wants to go to the real site because it's quite far and very difficult to access, and the area is very cold and site is very dangerous. So we can send some small batch of special engineer to capture the information, and then the engineers can sit back in the very warm area and very comfortable office to do the detection work. And as you mentioned, that how much it is to compare with the traditional work, I think the weakness of the current technology is that the accuracy is and the resolution is not as good as you go to the real site, and so we should focus on using multiple methodology to increase the reconstructed 3D scene that can make the very detailed information was included in the 3D model. And you mentioned the method on the crack detection. So I think this is a very good topic because for 2D image, we can detect crack very good, and for the 3D, it's quite difficult on the point cloud level. But we projected to 2D image that damage detection can be done by AI or by traditional human vision can do quite work. I don't know, did I answer your question or not?
Thank you very much for your explanation. Thank you.
Okay, thank you very much. So we have another question from the Sanji. Okay, Dr. Sanji.
Yes, Sanji has.
And also the Si Yulin, but Si Yulin, please wait for a while. Okay, Sanji, please unmute yourself.
Hi, how are you?
Hello, Professor Dang.
Hello.
Hi, Dr. Ho. Yeah. Thank you very much for the nice presentation. Yeah, it's been a while, like I didn't hear you. And then it's very fascinating to see the great work in the UAV. And actually, I'm quite motivated on your UAV work. So I'm getting the same here as well. Like I'm trying to do the point cloud base, especially for the base maintenance. We recently had a project, and then like you mentioned, yeah, we tried segmentation, but it was a huge work. So I mean, it gives you, like, for example, for the irregular cracks, or let's say the corrosions and these things, you can easily find the area, or let's say it helps for the quantifications. But sometimes from the YOLO, maybe we need a little more work to find the areas. But YOLO is quite fast and gives you very good results on that areas. So thank you very much for sharing that work. Thanks a lot.
Yeah. Thank you very much. So we still are in the developing position of this research. So so we hope we can do better in the future. As you mentioned that in detail measuring the damage area are quite important. And actually we did a lot of process, but a lot of people are talking about this. So I think this is one of the direction is like this. Yes.
Thank you.
Thank you very much.
Thank you. So how about Si Yulin? So please unmute yourself.
Hi, thank you, Professor Dao. Firstly, I'm sorry.
No see you.
Yeah, it's already 9 p.m. in Toronto. I'm not in my office, and this camera doesn't work, so I cannot turn it on. So, but I really enjoy your presentation. So I think your work is mainly based on computer vision. So I think from a physical perspective, many types of structure damage observed in the images also contain a lot of physical information. Nowadays, a very hot topic is physics-informed neural networks. So do you think it would be like feasible to include those information into the model training process? Like regarding the automatic captioning you mentioned, like could it be extended to explain the underlying something like the damage mechanism by physical laws, like the direction of the crack can indicate
so
the
actually
uneven settlement?
in my whiteboard we are considering about the use of PAN to do the structural damage detection in that area. So one of the topic is using the beam model to measure the wave propagation of the structure and use PAN to identify the structure parameter. But recently I find it's quite difficult to identify parameters like the shear modules of inside building or inside structures. We are working on it, but maybe next time I can have more bigger time to introduce you about the recent progress of our group. But I think it is possible, and but still it have a lot of difficulties. It depending on how to use it. I think PIN is a very useful tool, and a lot of people feels the charming of this technology. And I think there's a lot of work to do. But if you're interested, please go on to develop more on this direction.
Okay, thank you. Yeah, thank you so much, Sensei.
Thank you too.
Thank you. Since we have an active discussion, but the Urban Lifeline tell me we only have one
they
hour.
Get up in very late, I think.
I'm not so sure we can extend, but if there is no further question, I would like to conclude this seminar. So with a warm round of applause. Thank you very much, Professor Dan. Thank you.
Thank you very much. Very nice to come here.
Okay. See you. So.